Hello friends, today we are going to learn about the cloud computing architecture. In cloud computing architecture, we are going to learn about its conceptual view, logical view, deployment view, and cloud management. The cloud computing architecture of a cloud solution is the structure of the system, which comprises on-premise and cloud resources, services, middleware, and software components, geographical location, or commonly known as geolocation, the externally visible properties of those and the relationship between them. Cloud architecture are designs of software applications that use internet accessible on-demand services. Applications built on cloud architectures are such that the underlying computing infrastructure is used only when it is needed. For example, to process a user request. That means to process the user request, only it is needed. Draw the necessary resource on demand, like compute servers or storage. Performance or perform a specific job, then relinquish the unneeded resources and often dispose themselves after the job is done. While in operation, the application scales up or down elastically based on resources needs. The key element in comparing cloud computing architecture to other architectures such as grid architecture or the inclusion of a unified resource layer. The fabric layer contains compute resources, storage resources, and network resources. The unified resource layer contains resources that have been abstracted by virtualization. This layer presents the idea of resource virtualization offered by the cloud. The resources are converted to services at this layer. Infrastructure as a service is one example of the services offered by the cloud. The platform layer adds on a collection of specialized tools, middleware, and services. These tools can range from a cloud operating system to specialized softwares. Here, the application layer contains applications that executes in the cloud, and the application layer is connected directly to the unified resource layer. Now, this is the example for cloud architecture. It is a basic block diagram which shows that this is the application, it is the outermost layer, it is the platform, and then the unified resource and fabric. So, this is the bottommost layer, and then the unified resource, and then this unified resource, or I can say application, is connected directly to the unified resource and the platform in the architecture. Need for cloud architecture. What was the need for that particular cloud architecture? So, cloud architecture addresses key difficulties surrounding large scale data processing. In traditional data processing, it is difficult to get as many machines as an application needs. So here in traditional data processing, what happens is, if an organization or if any organization is having two of the machines for any application, now for the new application they need more machines. Say for example, they need 4 particular machine for that only application. So now what they can do is they will use the cloud services. If they are using the cloud services, they need not to worry about the physical data centers or physical machines which they have. But here in traditional data centers, it will be difficult for the organization to manage those things or those needs. Second, it is difficult to get the machines when one needs them. Third, it is difficult to distribute and coordinate a large scale job on different machines, run processes on them, and provision another machine to recover if one machine fails. See, here in cloud computing, we have replication of data, or I could say mirroring of the data. So, what happens when we have the mirror image of a data? If one of the machine fails, there is another machine to recover it. Now, if I am working on a traditional data center or traditional IT, what I had to do is I have to provision for another machine to recover if my one machine on which all of my applications are working is fails. So this thing, the cloud helps us to get out of this particular major issue. Then distribute and coordinate a large scale job on different machines. It is difficult for a traditional IT data center, but it is easy and it is easily done over a cloud architecture. Fourth, it is difficult to auto scale up and down based on the dynamic workloads. Fifth part is it is difficult to get rid of all those machines when the job is done. See, now if I am performing a job in a traditional data IT center or traditional IT data center, so I need more machines, I acquired them. As per the requirement, I have them, all those machines. But now, when my job is done, what will I do with those machines? So, it is difficult, or it will be difficult for me to get rid of those machines which I have purchased for that particular or that only application or that only job which is need to be done with that particular machines which I had bought. So cloud architecture solves such difficulties. That means I need not to buy those things, then I need not to get rid of it. Cloud architecture provide me with that option that if I need it, I will pay for that services, I will use it. Now when I don't need it, I will not pay for that services, and it is not there in my contract, or it is not there in the services included for my requirement. Applications built on cloud architectures run in the cloud where the physical location of the infrastructure is determined by the provider. They take advantage of simple APIs. APIs is application programming interfaces of internet accessible services that scale on demand, that are industrial strength, where the complex reliability and scalability logic of the underlying services remains implemented and hidden inside the cloud. The usage of resources in cloud architecture is as needed, sometimes ephemeral or seasonal, thereby providing the highest utilization and optimum bang for the buck. There are some benefits to building applications using cloud architecture. A few of them are listed here. First one is the almost zero upfront infrastructure investment. Second one is just in time infrastructure. Third one is more efficient resource utilization. Fourth one is usage based costing. Then potential for shrinking the processing time. First point which we have learned there, that is almost zero upfront infrastructure investment. It has following things like, if you build a large scale system, it may cost a fortune to invest in real estate, hardware, racks, machines, routers, backup power supplies, etc. Then hardware management. Now what is hardware management? It is the power management, cooling, etc. And operations personnel, the person who will operate those things. Because of the upfront cost, it would typically need several rounds of management approvals before the project could even get started. Now, with utility style computing, there is no fixed cost or startup cost. Second point is just-in-time infrastructure. Now, just-in-time infrastructure is, in the past, if you got famous and your systems or your infrastructure did not scale, you become a victim of your own success. See, victim of your own success, what does that mean? That more people are logging into your particular ID or wanted to buy that product from your organization or industry, but you are not able to scale that rapidly as per the demand is arising. Conversely, if you invested heavily and did not get famous, you become a victim of your failure. Here, you have a large setup, but now the product is not famous amongst the users or the people. So, this is the victim of the failure. By deploying applications in the cloud with dynamic capacity management software, architects do not worry about pre-procuring capacity for large-scale systems. The solutions are low risk because you scale as you grow. That means as the customers logged into your ID or as per the increase of the clients of the product, you can scale. And cloud architectures can relinquish infrastructure as quickly as you get them into the first place or in minutes. Next point is more efficient resource utilization. System administrators usually worry about hardware procuring when they run out of capacity, and better infrastructure utilization when they have excess and idle capacity. So, with cloud architectures, they can manage resources more effectively and efficiently by having applications request and relinquish resources only what they need, that is on demand. Now here, if I am working for a traditional IT data center, now the system administrator will be worried about the hardware. That means if he want, or that organization to which it is the system administrator, that organization wants more of the infrastructure, or they are running out of the capacity. They have the capacity of 100 logins and they are having 150 logins, so they are running out of capacity. So the person would be worried about the hardware procuring. And another one is if it has the better infrastructure utilization. That means if it has 200 logging capacity, and means they have access and they have 150 workers, so the particular person will be worried about how they can access those capacity which is had, or how they can utilize it in a more efficient way, the idle capacity which it has within. Next point is usage based costing. Utility style pricing allows billing the customer only for the infrastructure that has been used. The customer is not liable for entire infrastructure that may be in place. This is a subtle difference between desktop applications and web applications. A desktop application or a traditional client server application runs on a customer's own infrastructure, PC or a server, whereas in cloud architecture application, the customer uses a third party infrastructure and gets billed only for the fraction of it that was used. Now here, utility style pricing, what does it mean? That is, see for example, like if I am using the service electricity, so what is here mentioned, I am only paying for the amount I am using. Say for example, I used around 50 units of electricity, so I have to pay only about the 50 units of electricity. I am not paying about completely electricity generated there. The only amount which I am using, I am paying for it. In a similar manner, utility based cloud costing, cloud architectures, the person or a company has to pay only about, or only the amount that person is using. Next point is potential for shrinking the processing time. Parallelization is one of the great ways to speed up processing. If one compute intensive or data intensive job that can run in parallel takes 500 hours to process on one machine. With cloud architectures, it would be possible to spawn and launch 500 instances and process the same job in 1 hour. Having available an elastic infrastructure provides the application with the ability to exploit parallelization in cost-effective manner, reducing the total processing time. Some applications on cloud architecture, some of them are, there are plenty of examples of applications that cloud utilize the power of cloud architecture. These range from back office bulk processing systems to web applications. Some of them are listed below. They are, first one is the processing pipelines. What processing pipelines do? Document processing pipelines convert hundreds of thousands of documents from Microsoft Word to PDF, OCR millions of pages, images into raw searchable text. Second point, image processing pipelines create thumbnails or low resolution variants of an image, resize millions of images. Next, video transcoding pipelines. What they do? Transcode AVI to MPEG movies. Another one, indexing. Create an indexing of web crawl data. And next is data mining, which performs search over millions of records. Next point is batch processing systems. Back office applications in financial, insurance, or retail sectors. Then they are helpful in log analysis. Log analysis, they analyze and generate daily and weekly reports. Then nightly builds or perform nightly automated builds of source code repository every night in parallel. Another one is automated unit testing and deployment testing. What do? Is they test and deploy and perform automated unit testing, functional, load or quality on different deployment configurations every night. Another one is websites. Websites that sleep at night and auto scale during the day. Some of the websites like Facebook or WhatsApp or Instagram, all these things, they are software as a service. Now at daytime they auto scale. That means a lot of users log into it, they use it, but at night time they almost sleeps or there are very few of them who operates. Then another one is instant websites. Now for instant websites, websites for conferences or events like Super Bowl or super tournaments, we create websites, people log into it, use it, and after some time they are redundant because you are not using it again. So these comes under this websites. Other one is the promotion websites. Then comes the seasonal websites. Now what is seasonal websites? Websites that only run during the tax season or the holiday season, etc. Next is the architecture principles and guidelines. What are the principles and guidelines of cloud architecture? The first one is it contains high-level architecture principles that must be followed for successful cloud architecture. The following list is not intended to be an exhaustive set of cloud architecture principles. Instead, it is providing a starting point for the formulation of more specific cloud architecture platform or principles. First one is cloud interfaces and formats must conform to relevant industry standards. Second point is the system must present only the information in interfaces, etc., necessary to perform each specific function. The architecture should provide monitoring of all aspects of resource usage for the various dimensions required by both cloud consumer and provider. Another point is any cloud provider's claims of reliability, availability, security, and performance must be verifiable. Then next one is availability should not be limited by inevitable hardware failures. Another one is robust identity domain separation. Consumers of the system have no exposure to the consequences of other consumers' use of the system. Then, transparent architecture and control. Consumers have visibility into the design and operation of the system. Next point is improved productivity. It delivers an order of magnitude improvement over current levels of efficiency and productivity experienced in traditional IT environments. Then, assured data production or protection. So, consumers are assured of compliance with data privacy standards and regulations, have confidence that removal of data is absolute. Another point is automate operations. Now, consumers' runtime of business process services and platform services involves minimal manual operations. Next comes views of cloud architecture. First one is the conceptual view. The conceptual view of the architecture shown in the figure, or we'll see it later, brings together three cloud perspectives: the provider, consumer, and the cloud broker. This is the conceptual view of cloud architecture. See, it has cloud broker. So, cloud broker is doing the cloud brokering and cloud management. Now, cloud provider, it is providing the facilities. What are the facilities provided by the cloud provider? First one is the real estate, utilities, cooling, and others. Then it is also providing physical resources. What are the physical resources that are provided? They are the blades, disk, engineered, others. Engineered means engineered services which we are using. Then another thing which it provides is resource abstraction. What resource abstraction do? Compute, storage, and others. Then the services provided by cloud provider, it is the software as a service, platform as a service, and infrastructure as a service. Now, cloud provider also provide cloud management. So this cloud management has cloud operations, design type, orchestration, security and policy management, and cloud business management. This particular whole, the cloud provider which provides, is also known as access infrastructure, and then this is the cloud consumer. So it is the conceptual view. Conceptual view gives us the concept on which the cloud architecture is built. The role of cloud provider is the most important and most complex of all. Infrastructure for cloud is usually of unprecedented scale and stringent requirements. Implementing the cloud and maintaining it to satisfy the SLAs. SLAs is service level agreements of the consumers require extensive planning and precise execution. A cloud provider can spread the cost of facilities across consumers to achieve economies of scale. Facilities expense may include the cost of real estate, cooling, utilities, and rack space, among other things. The physical infrastructure components may include blades, networks, engineered systems, and storage disks. This we have seen in the diagram. These resources may be pooled and provisioned through grid technologies in order to support the elasticity and scalability demands of cloud infrastructure. The physical resources needs to be logically partitioned and secured in order to support multi-tenancy. Rapid elasticity requires the resources to be quickly deployed and undeployed at granular levels. Traditional deployments require downtime for scaling and maintenance, but cloud infrastructure does not have that luxury. The approach is to create and deploy new instances on the fly to grow, shrink, or fix the existing deployments. The resource abstraction layer provides the capabilities to logically abstract the physical resources. The service infrastructure exposes the cloud services to the consumers through the access infrastructure. Many resources can be offered as services, but the or a conceptual model defines three broad categories of services listed as below. First one is infrastructure as a service, platform as a service, and software as a service. These three of them are considered as the broad area, or you can say broad categories of services which is being provided by the cloud architecture. The diagram also illustrates a core concept that although there is an inherent ordering of these layers, there is no particular dependency between these three layers. That means they are not interdependent to each other. For example, platform as a service and software as a service may exist independently without the overhead of an infrastructure as a service layer. In this case, they would use dedicated infrastructure for running the platform as a service and software as a service. Alternatively, they may use any of the underlying layers. For example, a software as a service may leverage a PaaS service that is built on an IaaS service. It should also be noted that consumers may access any of these services through the access layer as indicated by the placement of the layer bars. The access infrastructure controls access to the services and provides the inappropriate interfaces to the consumers to access the services. Next comes the logical view. In the logical view, the logical layers and key logical components of the cloud infrastructures have. Second point is the access layer decomposes into two important sets of functionalities. They are interfaces and network components. The cloud needs a variety of interfaces to allow for access to the underlying services as well as its management capabilities. In addition to the end user facing interfaces present in the access tier, there will be several operator the specific capabilities present. Logical view. Now logical view can be understood by this particular diagram. See, it has three major things, that is resources, then comes the services, and then the access. Now resources have this logical pool, physical pool, and facilities. So facilities have this real estate, cooling, utilities, and other facilities, etc. That means then physical pools have servers, disk, engineered services, and other services. Logical pool have compute, network, storage, others, and external services as well. These external services have clouds, legacy, partners. Comes the services. Now, services as SaaS, PaaS, and infrastructure as a service. So, infrastructure as a service has server, network, storage. These are deployable entities. Then, PaaS, it has container, queue, and data. Software as a service has business process, business service, and application. This is connected to, these services are connected to resources as well as to the cloud management. This cloud management has business management. It manages with customer contracts, revenue management, etc. It has operations. It operates on service, life cycle, configuration, performance, monitoring, etc. Then security and management policy. or policy management. So it manages security, policy management, security services. Then comes the orchestration and mediation, and then the design time, that is model management and tools. Now this cloud management is again connected to this resources. Okay, so it manages the pool, so it is pool manager. Then coming upwards, this services is connected to access, and cloud management is also connected to access. Access has user interaction or self-service, and it is divided into two parts, that is interfaces and network. Now this interfaces have native protocol, portals, custom user interfaces, self-service APIs, and proxy, parameter security, naming, and balancing. So this depicts how the logical view of a cloud architecture is being built. We have seen the conceptual view, which creates the concept for the cloud architecture. Then comes the logical view. It gives us an insight that what should be the services and how it has to be operated. Then a common cloud management layer provides the management capabilities required for all type of services in logical view. A unified management framework provides a holistic view of the infrastructure and end-to-end visibility. The management layer provides support for both build time and runtime activities. Logical and physical pool of resources contain virtualized and physical resource managed by the pool managers. These resources may be fairly simple in nature, as the single virtualized server, for example, or complex, such as highly available or clustered Java application platform. That means it can be as simple as a single virtualized server and as complex as the highly available or clustered Java application platform. External resources may include third-party cloud services, legacy systems, and partner services. The service layer shows the concept of deployable entities that are self-contained